Before we get to the software that GPT generated for me, a quick explanation of how a CT scanner works is appropriate. Here we have an X-ray tube and a detector. The detector measures the output of the X-ray tube. These two are mechanically linked, so they move together. The X-ray tube moves across and fires a beam down, which is collected by the detector. It moves across again, takes another reading through there, and so forth. As it moves across, it takes a series of X-ray readings through the patient's skull, or whatever you happen to be X-raying. The whole system then turns through 1 degree and takes another set of readings, and it continues that for 180 degrees. So if you consider that halfway around at 90 degrees, the X-ray tube would be over here and shooting through to the detector, which will be over here. Then it would move down and again shoot through here. That's basically how the X-ray tube and the detector act. Okay, so at this point we have just an expanded explanation of the previous slide. We have an X-ray tubes down here. All the X-ray beams are going through here, and here's the patient with something that they're trying to observe. These are the detectors, and you will see that the plots of the output from the detectors reflects the amount of attenuation of the X-ray beam. That's in one direction, and then it'll move through to 90 degrees and do the same thing again, and you'll see that it gets a different response there because it's shooting through, and the object being X-rayed is halfway through the detectors. Again, if we go back through to here, projection number 3 is from the top, from 0 degrees. It shoots through and we get another response here, which is dependent upon where the object to be X-rayed is. And again through projection number 4, shooting through from the right hand side into the detectors on the left, and we get this response here from the detectors. Okay, at this point then, all the data that is collected is stored in a file called a sinogram, and this represents the four main views that we've just taken: position 1, position 2, position 3, position 4, and it traces out a diagram like that. Of course, there are readings taken in 1 degree increments right throughout the whole scan. So here we are at the back projection, and this is where the image will be reconstructed from the projections. Again, we're only showing 4 projections. There are normally at least 180. Now this is a response from the detector in each of the positions, which we saw in the previous slide, and this value here is divided up into however many pixels there are across the image, and it is assigned, if it's 128 pixels, it's assigned 128th of this particular value. Again, same thing happens here. It's always a square image, so it's across that way, and that way. So after 8 projections, this is from 0 degrees, 45 and 90, we start to see an image forming, and then after many projections we get this result here. As you can see, it is blurry, but at least we can see the image. So again, as from the previous slide, we have this simple back projection. This is our object being examined in the middle of the picture, and this is a response from the detector. And if we back project across those, we get an image in the middle, but it is blurred. So what we do then, we filter the response here from the detector, we multiply it by this function here, or convolve it with this function here, and we end up with this response. What this is doing is modifying the output from the detectors to a shape like this, which will give us a much better and less blurred image. That's the simple explanation for how a CT operates. I thought I'll get it to write code to generate a square image of 128 by 128 and see what that did, and it came up with this little bit here. So I'll copy the code from there, go into Python, run the code, and up she comes with a whole lot of data. That's not what I wanted, so I'm back to GPT, and I said modify the code to plot the matrix. So it generated this code, so I'll copy that, go back into Python and put that code back in. Now we'll run it, and there, and lo and behold, there is the image that it generated for me. Now that's with no input from me other than asking it to do something for me. I haven't put any sort of coding in there of my own volition. So progressed a bit further and asked it to modify the code to generate a sinogram from the image and plot the sinogram. It immediately generated the code, and I'll copy that code, go back into the Python, replace the code there, and here it gave me a sinogram. Now I know that that's not a proper sinogram. What that is a plotting a value of the black area up to the white area, down, and that. So I told that's not correct. So I went back into and modify the code to do 180 views for the sinogram and plot both image and sinogram. And it came back up with a slightly longer code. So I'll copy that, go back into here, wipe all that, put the new code in, and do that. We're not quite there yet. We're not quite there. We got the original image and we got the sinogram, but the sinogram is still not correct. So back in. So all I said was, in this code, sinogram is not rotating at the proper angle. So it comes up and says, apologies for the confusion. The sinogram generates the previous to generate the sinogram. We need the radon transform, and this is where it brings it up by itself without me prompting it in any way. So we'll copy that code once again. It's giving me new code, which is getting slightly longer with every iteration, but still very short. There we go, and we do that, and all of a sudden here we have a CT image which is essentially correct. So after about an hour and a half between ChatGPT and myself, we iterated backwards and forwards, and I learned to ask better questions and better explain myself to the program so that it could write the final program. This is what we ended up with. I have modified it only very, very slightly. One of the things that I have done is I've made a couple of images in a photo editor, a drawing program, that I can demonstrate the CT function on. The first one is this Shep Logan here, which is an official CT test phantom. So we'll just run the program on that. And there we see the original image, which is the one I obtained, the sinogram of that image, and then the reconstructed image. Now the reconstructed image is of much less contrast than the original, but that is purely due to lack of development of the program. The thing has reconstructed properly. As you can see, it's got all the bits and pieces in the phantom are showing up properly in the reconstructed images. The sinogram is being sharpened. The sharpening figure here is given as 2. So the next one is this one, which is just a pin phantom. Again, it's something that is done on CT for testing purposes. It's just a black background here with a white dot in the middle, and you can see the sinogram quite clearly as the thing goes through. And the reconstructed image, it is a little sharp. That's shown by the jump from the black to the white between at the interface here. The next one, photograph of a girl, and here it is in all its glory. This is a photograph I obtained off the net, the sinogram of her, and this is her being reconstructed. So the image was taken, broken down into a sinogram, and then the program reconstructed the image from the details that were in the sinogram. And as you can see, there are a few artifacts here, but that's purely the difference between the real world implementation of this software and the actual simulation that I'm using here. As far as I'm concerned, it's doing a sterling job. The last example I'll show you is again the girl, and I've put her in a much wider black area here to try to get closer to real world, and as you can see, a lot of the artifact is gone. There we go. I was able to make ChatGPT write some software that I certainly would not be able to at my level of expertise in Python.